In this video, we will talk about standard error. As you remember, error in statistics doesn't mean mistake. It has to do with variability. So what is standard error? It is the standard deviation of a sampling distribution of any sample statistic. Usually, it is our estimate of that standard deviation. The most common example here is the standard error of the mean. By this definition, the standard error of the mean is the standard deviation of the sampling distribution of means. Let us look at this in an illustration in order to understand it better. Here is a population of imagined heights of people with a mean of 175 centimeters and a standard deviation of 10. These are not real data. Let's say we want to estimate the population mean by drawing samples of 25 people. So we pick 25 people, we measure their heights. Here's our sample, and our estimate for the mean is 172, and our estimate for the standard deviation is 10.8. What if we draw a second sample of 25 people? Here's that new histogram and the new estimates for the mean and standard deviation based on the second sample. What if we draw a third sample? That's our third sample and the associated estimates. Now we got a low estimate for the mean and low estimate for the standard deviation. It's just random sampling. Let's try a couple more samples. Okay, so this is taking a long time and it's gonna look like a mess. So let's skip this step-by-step process and go directly to sampling 1,000 times. So imagine 1,000 different samples of size 25 drawn independently and randomly from this population. That's the result. As you can see, most means end up around the true value of the parameter, but there is a big range here, and the distributions are also like a bit all over the place around this general shape. Let us create a histogram for all those means. The histograms of the means of samples of size 25. That's it. This is the observed sampling distribution for our 1,000 means. This is an actual simulation, so it's not perfect, but it's pretty close to normal, and it has its own mean value and its standard deviation. So the mean of all the means and the standard deviation of all the means of these different samples. So we can actually calculate these values. We have the numbers, and the mean of all the means is 175.1, which is very close to the population parameter. And the standard deviation of all the means is about 2. It is no accident that it is about 2. 2 is 1/5 of the standard deviation of the population. And it turns out that the standard deviation of the means is actually given by the formula standard deviation of the population divided by the square root of sample size. So sample size here is 25. The square root of 25 is 5. So 1/5 of the standard deviation of the population is what we theoretically expected and is what we got. What if we had used samples of size 100? So let's draw 1,000 samples of size 100 instead and do the exact same thing. Here are the results. These are all our means from the samples of size 100 drawn from the same population, their histogram, They're normally distributed. Their mean, so the mean of means is 175.15 for this simulation, and their standard deviation is about 1. The observed standard deviation for this distribution of means is 1/10 of the standard deviation of the population. Why 10th? Because the square root of 100, which is the sample size, is 10. And so its standard deviation divided by 10 is what we expect and is what we got. In general, the standard error of the mean is the standard deviation of the sampling distribution of the mean, or more usually our estimate of that. So we use the same term to refer to the population or to our estimate. The standard error of the mean that is theoretically expected, which is based on all the possible samples drawn from the population, all the possible samples with same sample size, is equal to the standard deviation of the population divided by the square root of the sample size we are using. Our estimate for that, which is the observed standard error of the mean, is the standard deviation of our sample, which is the only thing we've got, divided by the square root of the size of our sample. So we can see that the standard error of the mean theoretically depends on only two things: the standard deviation of the population and sample size. In practice, because we never know that, we only know the standard deviation of the sample, this is what we use to estimate the standard error of the mean. And this means that our estimate of the standard error will be good only if we have a large sample size so that we can trust our estimate of the standard deviation. What are the implications of this? First of all, we know from the central limit theorem that our means are normally distributed. And now we know what their standard deviation is. That is the standard error. We know how much it is. This means we can now link to probabilities. And in other words, this means that in 95% of samples, the sample mean will lie within 2 standard errors away from the population mean, roughly speaking, but this is a useful approximation. Let's say that again. We only have one sample, but we should always think about all the other possible samples that we didn't use. So thinking about all possible samples, in 95% of them, the sample mean will lie within 2 standard errors away from the population mean. That looks like magic. We now have a sense of how far from the population mean we can be. And to do that, we only needed the sample size. So the sample mean, our estimate of this statistic, comes with a free gift. Statistics gives us the free gift of a range that indicates how far off we may be. And that is given by the standard error, which depends on sample size. The second implication of this formula is that because of the square root in the denominator, if we want to increase our precision in the estimate of the mean by a sample of 2, so if we want to be twice as precise, we need a large sample that is actually 4 times as large. So twice as precise, 4 times as large sample size. Let's look at this a bit in more detail. How is standard error related to sample size? This is the formula for the standard error. In the theoretical, that depends on the population standard deviation. So the standard error of the mean in its sampling distribution is equal to the standard deviation of the population divided by sample size. And for a given standard deviation, let's say we consider samples of size 16. So all the possible samples we can draw with size 16 will have a standard deviation equal to standard deviation divided by the square root of 16, which is 4. So for sample sizes of 16, the standard error will be 1/4 of the standard deviation of the population. So remember, this is the standard deviation of the means of the samples, and this is the standard deviation of the members of the population. So it's of the data. This is not of means. The standard deviation of the values in the population divided by 4 gives us the standard deviation of the means of samples of size 16 drawn from this population. What about sample of sizes 64? If we do the same thing, because the square root of 64 is 8, then we find that those sample sizes lead to a standard error of the mean equal to 1/8 of the standard deviation of the population. In other words, we have quadrupled the sample size, but we have only halved the standard error. So we have increased the sample size by a factor of 4, but have only affected the standard error by a factor of 2. The importance of the standard error lies precisely in the link to probabilities, because of this magical sentence here. In 95% of samples, the sample mean will lie within about 2 standard errors away from the population mean. Of course, you don't know if you have drawn a sample that is in that 95% or in the other 5%, but you can calculate the standard error and give an interval or range of values where you expect the population mean to be, and then you'll be correct 95% of the time. And that's very good. More generally, going beyond means, 95% of the time, any statistic will lie within 2 standard errors away from the population parameter it estimates, as long as the sampling distribution of this statistic is approximately normal. And if it isn't, we can still link any desired probability to standard error via whatever the corresponding distribution is for the statistic in question.